Okay, yo, we're back, everybody. And we looked at polarity of molecules last time around. We looked at polar molecules, dipoles. We looked at the two types of intermolecular forces. We looked at the polar molecules or dipoles. We looked at hydrogen bonding, and we also looked at the London forces as well for nonpolar. This next lesson really is finishing up with some examples of that, and then looking at some other types of covalent bonding that are certain molecules that maybe are little exceptions, or we kind of fill in the rest of some compounds that we see that have different types of covalent bonding to them. So again, we can look at in terms of polarity. We can sometimes have this little play on words or a little phrase which is like dissolves like, and the like part of it means the polarity of the substance. All right, so if we take a look at this through this thing, you'll see I took this beaker here and I separated it into a polar layer and a nonpolar layer. Okay, and what we find is that polar layers or polar molecules tend to stick to each other because of their polar forces, right? The dipole forces. But nonpolar materials don't mix with those polar because they don't have those plus and minus ends to them. So we can kind of take a look at what types of materials would have nonpolar forces and what types of materials would have polar forces. So, what we find is that these two types of molecules won't mix too well or not mix at all when you put them together. All right, and the word for this is immiscible. So immiscible simply means that they won't mix. Okay, so what kind of things would dissolve in the nonpolar layer? And you can almost think of this as becoming almost like an oil layer or some type of nonpolar layer. You can think of this as maybe an oil layer, maybe. I guess that's the best way to think of it. It doesn't have to be oil, but it could be some type of oil-based hydrocarbon. Okay, so CH compounds. CH compounds are hydrocarbons, and hydrocarbons are a class of compounds that contain only hydrogen and carbon. And because hydrogen is all the way around the molecule, you're not going to have different charges. So because of that, hydrocarbons are all going to be nonpolar. Okay, number two, anything that's symmetrical. And we talked about SNAP, right? So symmetrical molecules will cancel their polarity. They will also be nonpolar. All right, any type of fats, oils, plastics, greases, waxes, these materials a lot of times have hydrocarbons in them or are hydrogen bonded or have hydrogen bonded to them on the outside. So again, and a good example of that here would be if I showed you, a good example would be the molecule butane. Butane is a molecule that has hydrogens all the way around here and is also symmetrical. So these hydrocarbons typically have the same element you can see bonded all the way around, and because of that, become nonpolar. All right, and again, so all of these would generally dissolve into this nonpolar layer. Now, if you go to the polar layer, what kind of things or in real life would be dissolving the polar layer or mix with the polar layer or attract to the polar layer? Is sugars. Okay, and typically we're talking about glucose and sucrose. Again, sucrose is table sugar, regular table sugar, and of course we should know what glucose is. These are the two good examples of two sugars. Okay, alcohols. Be really careful with alcohols. Okay, alcohols are a carbon atom that's bonded to an OH group. Okay, covalently bonded. A good example is the simple alcohol methanol. So if I draw methanol should look like this. It would be a C bonded to a C, bonded to an O, bonded to an H. We put our little lone pairs there like that, and we finish this with H's, and we can see that's an asymmetrical molecule minus charge here. All right, asymmetrical. So alcohols, an alcohol, they have a C bonded to this OH group here, is that's what makes it an alcohol. Okay, any asymmetrical molecules, again, that's going to be your bent, your pyramidal. Okay, usually bent pyramidal molecules are typically asymmetrical. Okay, those will be polar. Okay, any soluble ionic compounds. Okay, soluble, we haven't done that yet, but that's going to be something you can look up on table F. Don't get crazy with this yet. Ionic compounds, again, will be a metal and a non-metal. Okay, so simple ionic compounds like sodium chloride and calcium bromide, maybe. Okay, things like that. Those materials, these simple salts like this, generally will be, maybe you want to think about potassium iodide, maybe. Okay, any of your alkaline metal salts here will be soluble. All right, so that's important to know. Okay, so basically, polar molecules, okay, will strongly attract other polar molecules. Again, another word for polar molecules is, you guessed it, dipole. Okay, same thing, with their positive and negative ends, but will not attract to nonpolar molecules. So that's why you get this separation. Okay, mixtures then separate into layers. Okay, or the unlike polarity molecules repel each other. Okay, waterproofing sprays and waxes are a good example of nonpolar layers that repel polar water. All right, so again, you can spray this waterproof stuff on your clothes sometimes, or you can have a wax your car. These kind of things will prevent water from penetrating things. All right, and again, we'll skip this little thing here. Okay, um, coordinate covalent. Okay, coordinate covalent, again, is not really a type of covalent bonding. This is a very small topic. I don't want you to get crazy. Okay, typically speaking, what we find is that one element contributes both electrons to a shared pair. A good example is hydrogen. Hydrogen has one dot, another hydrogen has another dot, and typically what happens is, what do? We put the dots together, or we link them, and then we get a typical covalent bond. All right. Now, the key to this is the fact that one element brings one dot, the other one brings the other dot, and they share the pair. All right. That doesn't always have to happen. Sometimes we find molecules where a different explanation is needed. Okay. So in a coordinate bond, we look at the source. Where did those electrons come from? Was it one and one? Okay. Or was it something slightly different? Okay. And this is going to happen in polyatomic ions a lot of times. So many of the polyatomic ions, good example is NH4, okay, and H3O plus, where you're going to have this, coordinate bonding. Okay. So for example, if I take an ammonia molecule being NH3, and this is a neutral ammonia molecule, what you're going to see is at the top of this is going to be a lone pair. Okay, and that's where going to be a lot of negative charges, right? Not only is nitrogen 3.0 and hydrogen is 2.2, but you also have a large lone pair up here. So this is a very negative part of a molecule. All right, and if you have hydrogen ions, okay, and a hydrogen ion, again, is simply a proton that doesn't have any electrons. So you think of it just being H. What this H can do is attract to the pair of electrons here and actually form a covalent bond to it. All right, so you have to think about is that, let's just say you had one hydrogen with no electrons and element X that has two, you could take two electrons instead of being one and one. All right, so what that hydrogen will do is it'll jump on top, okay, and will form NH4 plus, and NH4 plus will now have a bond here, a bond here, a bond here, and a bond here, where this new bond was then formed. Okay, the key is this case. So what we find is that all of these bonds are identical. So it's really just the source that's different. All right, so you really don't have to sit and draw these kind of things and be able to draw it out on which elements get what electrons. We're not interested in that. What you want to know is that some molecules have this in it, and that's how we explain some of the bonding. All right, and these are your best examples right here. So if you're looking, for what's on the test kind of thing, which I hate, doing all the time, but I'll do it in this case. These are the best examples. All right, and the last example here for some special type of bonding is something called network covalent. Now, a network is a computer network, right? Think about a computer network where you sign on at one laptop, or you can sign on a different laptop in another part of the building, and they're all connected. So you have to think of these as connections, okay? And a network bond or a network solid is an extensive system of covalent bonding. So you're not talking about individual molecules here. You don't have separate molecules. And because of this, those linking of those covalent bonds is extremely strong. Okay, and when it's very strong, it's going to give you extremely hard solids and very high melting points. Okay, which is not typical of covalent bonding. Okay, typically covalent bonding is going to have low to moderate melting points. This is a special group. Okay, they're often used as abrasives. Okay, which wear down other materials, and use as cutting tools because they're so hard, you can cut very easily. So the hard solids actually gives you the properties. So the bonding gives you the structure, which is your network, which gives you your properties, which gives you your functions, right? Okay. The best examples are going to be the following: quartz and diamond. So again, you're looking at the group 14 elements, okay, specifically here. Diamonds, very, very hard substances. You can see here that you have this, the diamond is that one carbon is bonded to four other tetrahedral carbons, which extends for long distances over the course of the whole molecule. Sometimes they actually call this a macro molecule because it's repeated units of this connected together. Okay, and to just give you an idea, it's shockingly high melting point. Okay, diamond has a melting point of 3,500 degrees Celsius, which is way higher than any other molecule, any other compound that you generally have. All right, so that ends the show on this one. Okay, and we'll get ready for the next one. Thanks a lot. And there's the bell.